thank you for having me today. I'm super excited to talk about constructability with you this morning. I also want to thank my students listed on this slide here. I've got a number of amazing students that worked here, and some of them are in the audience today. So a big thanks to them. Thanks for coming out and seeing this work. We're going to talk about determining the effectiveness of curing concrete, something that people don't talk a lot about, and we will specifically get at walls and what it means to you. Now, the people that funded this work are DOT folks. They care about durability deeply. That's very important to them. Now, you may not. That may not be as high importance to you. I get that. Hopefully, you can still take away something from this presentation and realize how curing impacts the quality of your concrete. Well, Ken Hover taught me many years ago that there's 3 key to successful concrete: the initial cement grain spacing, the final cement grain spacing, and promoting reaction. What's this guy talking about? Initial cement grain spacing, that's all about water-cement ratio. How can we bring those cement grains together before they start to react? Final cement grain spacing, even though you have a great water-cement ratio, that doesn't mean you consolidated, you finished, that you've prepared that concrete correctly before it gets hard. And then the last one, promoting reaction, that's what we're going to talk about today. That's all about curing. Now, I'm showing 2 concretes here, one on the left, one on the right. Both of them have the same water-cement ratio. What? This box is supposed to be like concrete. The clear stuff, the white, is like water, and these are little cement grains. Now, over time, as this, oh, you can't see my little mouse, can you? Oh, I can see it up here. I did a great job up here. I guess I have to you can't see anything over that way anyway. All right, awesome. So those little grains that I was pointing at you couldn't see before are cement grains. And what we're going to do is now we're going to make them react. Oh my gosh, the beautiful gray. The hydration product, the calcium silicate hydrate shows up. That's the stuff that we care about. We get good curing on the left, not so good curing on the right. Can everyone see the difference in the gray? Please, come on. Can you see the difference in the gray?
Yes.
Oh, good. Because when I start to load this system, the system on the left, because there's more gray, because there's more interlocking between my grains, I'm going to be able to easier to distribute load. That's why it's stronger. System on the right, not as much gray, not as much interlocking. Therefore, the load is restricted to limited paths, so it's not going to be as strong. Now let's talk about water. Let's talk about outside fluids trying to penetrate into our concrete. The one on the left, again, lots of gray. That's good. Hard for the outside stuff to get in. One on the right, look at that. Look at that. This water's just pouring through it. And the easiest way to summarize this, the way to make this easy, it's all about straws. Now, some of you are drinking coffee. I see you. It's early in the morning. I get that. When you drink coffee out of one of those very thin coffee straws, you got to work real hard to get that solution up. And that's good because you don't want to burn your mouth, right? And that is like good curing. And the system on the right, that is not so good curing, and that's like those big McDonald's straws. You know the thing you can drain a cup in about a second if you pull on it really hard? And that is what poor curing is all about. So in summary, as curing improves, the mixture will be stronger. It will have a lower probability, and a lower permeability, and that is a good thing. It's all about the straws. But I'll tell you what, your concrete can be compromised if it's not properly cured. That means you can have the best mix design. You can have the best construction practices, but if you don't cure it correctly, you're not ever going to reach its potential. And I talk to contractors all the time that say, concrete, and we never cure it. How do you know how great your concrete could be? Huh? How do you know? Because they can do amazing things. Last week was my daughter's 16th birthday. I've got no curing cake on the left. If I served that cake to my daughter, I would be ostracized, kicked out. I couldn't have come to the house for a week. It'd be horrible. But the one on the right, look at that. Oh, the frosting, the cherries, that's what curing's all about. If I tried to buy the house on the left, the uncured house, well, the one with no cladding on the outside, it just doesn't look right. It's not what we want, but the product on the right, that is what it's all about. Now let's get to concrete. This is a scanning electron microscope image of a poorly cured concrete sample. What I want to show you here at the top, which you can't see because I forgot the mouse doesn't work, but maybe you can see at the top that there's a lot more white particles. Those white particles are unhydrated cement grains. You wasted your money. That cement didn't do what you want it to do. See all the cracks up there at the top compared to the bottom? That's why we say the top has a compromised surface, a compromised skin. Some would argue that skin is the most important part for durability of our concrete. So now let's get into something we care about, walls. Talk about walls today. So I have this question. If my concrete is strong enough, as in if it's able to hold its own weight, Can we just remove forms? Is that okay, just to take them off? And how does curing choices impact the life of the concrete? I'm going to answer those two questions today. So contractors in the state of Minnesota, and I know other places as well, but that's where this initiated from. We're like, we want to cycle our walls in the field for bridges. We want to cycle them every 12 hours. Makes sense. They want to get high production out of it. The concrete's got sufficient strength, but when we take the walls off, when we take the forms off, we're going to not cure it anymore. Does that reduce the durability? So we're going to investigate this. We're going to do two different phases. In phase one, we're going to look at the effectiveness of different forming materials. We're going to compare wood to steel to rubber for being on the surface at 12, 24, and 72 hours. In phase two, we're going to try to use different curing methods to extend the curing. That means if I have to remove the wall at 12 hours, if I have to take the form off at 12 hours, I get it. Sometimes that's what you need for your schedule. I get it. What can we do to extend that curing or try to help with that situation? And how much life do you end up losing? Now, we're going to look at a limited data set today, testing a typical wall mix, 0.45 water cement ratio, 20% Class C ash, 6.5 sack mix, limestone and natural sand, about a 5-inch slump. So how would you test a wall? Well, you can make a wall, you could take cores, you could try to investigate it, or you can just test a small piece. Just a piece. What we're going to do with that is we're going to make a smaller form here, or a smaller sample here that's 4-inch by 4-inch by 4-inch cube. We've got an impermeable membrane. That means it cannot lose water out of that blue surface, but it can on the form surface. I know this is a little bit strange. See what's going on. What we're trying to do is simulate that piece of that wall, because that piece can't lose water up, down, can't use up, can't use down, can't lose it to the left, but it can lose it to the right. Does that make sense? That form surface is what it is all about. So we make these 4-inch cubes. Phase one, we're going to test the steel, wood, and rubber. Phase two, we're going to look at how we can use steel forms and then extend the cure. This is what our samples ended up looking like, something like this. There's the finished surface there to the right, and there's the impermeable membrane around the outside. And remember, it's all about these straws. Think about these straws. If we have be hard for that surface to lose moisture. And it will be hard for that surface to uptake water from the outside, and it will be hard for that surface, for chlorides, outside nasties, to get into our concrete. And remember, it's all about the straws. And we're going to just use step one here for phase one. That's where we compare the different forms. So what am I talking about here? Well, in stage one, we're going to look at drying. So we're going to, after we've made our samples, we're going to put it, as soon as we pull the mold off, we're going to put it into a drying environment, 50% relative humidity, 73 degrees Fahrenheit for 28 days. Then we're going to drop it into water. We're going to take this dry concrete, drop it into water. What's going to happen? That is the sound if you get close enough. If you get close enough, you can hear that pores, that straws sucking that water in. That's what's going to happen in stage two, and we're going to measure the mass change. Then we put it in some chloride solution, and we're going to measure and look what the chloride profile looks like after 35 days of ponding. So here's our step one. We're going to measure this mass change. Here we go. Let's see how it changes over time. So on this plot, the x-axis, the top graph here, is time in days. The y-axis is the mass change. So let me think. Straws. Which one's the best cured system? Is it the lowest one or the highest one? Who can help me? Dead silence. If I have small straws, it's going to be hard to lose moisture. You right? You agree? Yeah. So the one that's higher up, the wood, means it did a better job of curing compared to the steel or to the rubber. That's at 12 hours. Here's what it looks like at 24. Same trend, just moved up a little bit. Here's what it looks like at 72. Whoa. As it goes up, is that good or bad as far as curing goes? Me, please. Good. I didn't hear you. Help me, please. Good. Oh, that's good. You got it right. That's good. 72 hours, cured it longer. It's getting higher and higher and higher, and they follow the same trends. So the samples are losing water as they dry, losing mass, right? And the better cured samples are going to lose less mass over time. And the wood forms seem to be the best followed by steel, followed by rubber, but there's not a massive difference between the two, or between the three. And the longer you cure the sample, the less moisture is lost. This shows that extended curing in forms will help resist water loss, this drying that happens. This means the concrete should be better at resisting outside chemical penetration, and we will check that coming up. So, and while there's some differences between these different form surfaces, they're not that large. But for phase 2, we're going to look at this really practical method, this really constructible idea here, that if I have to strip at 12 hours, if my schedule demands it, what else can I do to extend my curing? And I'm going to do some things that are impracticable, some things that are non-constructible, but we need to look at all the variables that are out there and compare them. We're going to look at sealed cured for 1 day, 3, and 7 days. We're going to look at wet curing for 3 and 7. We're going to look at different curing compounds and how they perform on the surface, and also just leaving the molds in place for 24 hours and for 72 hours. And this is kind of what the data looks like, the drying data. And remember, the highest one is the better performing. You agree with me? Yeah? Awesome. So we have our molds for 72 hours at the top. And look at the bottom, molds for 12 hours. Falls exactly like we'd expect. The plastic, the curing compounds are up at the top. And then the wet curing. What? What? Wet curing, the gold standard of curing at the bottom? I'll talk about that. Hold your horses. We're coming back to that. The sample that was cured in the steel molds for 12 hours did the worst. For 72 hours was the best. And the samples that were sealed for plastic for 3 and 7 days did a pretty good job. But also those curing compounds, they also did a good job. And we'll talk more about those coming up. And the wet cured samples, though, did not perform well at all. And this is probably because the burlap did not hold the moisture on the surface of the concrete. What? What is burlap for? Potatoes, right? Hauling potatoes around, right? That open system of material just didn't do a great job. When we put the wet burlap on the top, we put plastic on the outside, this water wasn't held on the surface. It fell down. And I think you see it in the field all the time. If anyone was crazy enough to ever try to wet cure a vertical member, I'm not saying that's ever going to happen. But you have to show people sometimes that even what they think is going to be true may not really be true because of constructability. I think that's really important. Samples up. We looked at the chloride penetrations inside, and to do that we used a very fancy microscope. This basically takes chemical maps of the surface of the concrete after it's been ponded with chloride. So we dried it, put it in water, put it in chlorides. I'm not showing you all the data, I'm just showing you part of it, but we get plots like this, or maps like this. The black spots there are aggregates. They don't have any chlorides in them. They're aggregates. The dark gray has very, very low chloride, almost none, background. And then the blue, that's where the chlorides are. And you can see on the left, less blue. On the right, more blue. You with me? Same concretes. The only difference is the curing. And because the curing's not as well on the right, then this material is penetrating more. So next we can digitally cut the sample up in different layers, actually quantify the amount of chlorides at each layer, just like if anyone sadly had to powderize concrete and actually measure the chloride content. We're doing the exact same thing that you would do in your lab. We're just doing it digitally. And data looks like something like this. This is the solid line is what if you did the powder test. The dashed line, the little crazier looking line, is where if you use the microscope. They're pretty similar. They compare pretty well. Now we're still working on this. Amir, who's in the audience today, is cranking on this, and he is working hard to improve this and actually has some great improvements to some of this data, but this is what we looked at and had in our original Minnesota DOT report. This is what the samples looked like, and from these lines, you can get things called diffusion coefficients, and you can use things called service life models. You have to be a little bit careful using a service life model, but that's what Minnesota DOT wanted, and so that's what we did. And this what tells you is that, for example, if I left my molds in for 24 hours, right, I may have to just come down here and talk to you, right, take this to the audience so I can actually point to something. At 42 years is what the service life model says, 42 years. If I'm in Minnesota with 2 inches of cover with epoxy-coated rebar, that's what the model says, with chloride being the limiting thing that limits its life. What this says is these curing compounds, sealed curing, you get about 35 years. That's about 20% loss in life. That's what that says. You lose 20% of your life compared to you leaving the forms on to use these other curing methods. Strip for 12 hours. The wet curing and the just stripping mold, 12 hours, you lose about 1/3 of the life of the structure. 4 chlorides with a 2-inch cover, epoxy-coated rebar in Minnesota. That may not be your project, that may not be what you're about. What that shows, though, is for certain people in certain locations, curing is extremely important. So based on the service life, there we go, you can increase your service life by about 36% if you leave the molds on for 24 versus 12. I get it. It's not constructible. It might not work for you, but that's what the numbers say. If you got to strip it 12 hours, curing compounds are a great solution. You should be putting them on, right? And or putting plastic for 3 days. I get it, may not be constructible, but you can do it. And that reduces your service life, if you want to do that, for about 20%. So the wet curing samples didn't perform well at all, and this is likely because the burlap just wasn't able to hold the moisture on the vertical surface. What does this mean? Curing does impact the durability of the concrete, at least with the materials that we looked at in the situations that we investigated. And if the concrete durability is important to you, then you should leave the forms on that for as long as practical. And if you remove forms early, then you can use some kind of curing compound on the surface to come back and extend life. So in conclusion, curing is an important part of the construction process that's often overlooked. And I think it's overlooked because people don't understand how important it is. All right? Just because the concrete is strong does not mean it has stopped reacting. And not all curing methods are created equal, and they should be chosen based on the long-term needs of the concrete. So if you have any questions, I'd be happy to take them. This is my website. Also, I make YouTube videos. Yeah, YouTube videos all about concrete. I get anywhere between 5,000 and 10,000 views every single day from people all over the world. And I do this because I want to help people learn about concrete. That's what I'm all about. So you can find me at youtube.com/Tyler Lay. Please like, subscribe, and leave me a comment. Take care, everybody. If you have any questions, let me know. Thanks. Sure. There's a paper that's in the works. My students have done all their job. They have put all the hard work in, and I'm the final step. But if it goes out there, this is a sensitive subject. This is an important subject. Constructability is critical, and we need to make sure that we state the findings carefully so that they're not overextended and people just require wholeheartedly that this everywhere. Because one has to think carefully, where do I need durability and where do I not? The answer is I don't need it everywhere. On internal walls in this building, I don't need it, right? So this wording has to be done very carefully to make sure that we don't cause more problems in our industry and instead just try to bring education and knowledge to what we're finding. Does that make sense what I'm saying? But that is going to be eminent, right? And thank you for that question. Anything else? Sir.
I suppose we're supposed to use the microphone, but so I currently have a project where we're trying to decide why there's a difference between the cylinder strengths and cores that we've cut through full-scale structural specimens. And so in hearing what you're saying, it sounds like these cylinders were cured in plastic sleeves, and they were supposedly kept wet, but we're not sure that they were. Were cured in plywood forms. So I guess the question is just the plastic alone sounds like from what you're saying in this presentation, the plastic is going to have a influence on the curability or the durability of the resulting cylinders?
Okay, so let me slow down there. So are the cylinders lower strength than what you find on your walls?
So these are actually happen to be slabs. So
Okay.
they're horizontal walls.
Okay, are the cylinders lower strength than what you find in your slabs?
Yes.
Okay.
Much lower.
So my experience is that that's probably not a sleeve, a plastic versus a wood forms. It's probably not.
Okay.
It may be something to do with the handling of the cylinders,
Right.
or the curing methods that they use for those cylinders. I would probably go out there and look heavily. Maybe it's too late. Maybe you can't do anything about it. But in place concrete strength makes me feel a lot better than cylinders.
Yeah.
But I would carefully about how those cylinders were handled,
Yep.
and that may be an indication of what was going on.
Right, because if they were dropped or they were handled inappropriately in the first 2 days, that could.
Yeah,
have an
or if they
influence.
weren't cured correctly, as in they were allowed to get super hot or super cold, or
They
if they
got
didn't,
hot, we know that.
if they didn't stay wet. And that's a really important point, is that oftentimes the handling of our samples have a big impact on what decisions people make. But I'm glad that you cored, and I'm glad that you got some kind of ground truth type info. So that's what I'd
Okay.
say. Thanks a bunch. Yeah, appreciate it. Oh, you got one more? Do you have time for one more?
Yeah, I'll stick it as you talk.
Sir?
I just wanted to ask you, what's your opinion about why the wood was a better curing material than the plastic or steel?
Good question. And I'm not sure if all wood's created equal, right? And I'm not, but I think that wood soaked in some water, right? At the surface. We did form oil it and everything, but I think it did hold some water there longer than what the steel did or the rubber did. But I'm not certain of that. Thank you for the question, though.
That also brings up something interesting for those of you that do shotcrete out there, because shotcrete, you don't even have that initial cure of the wall.
That's true.
So I don't know if you've looked into that.
No, I'd love to, but there's no reason someone couldn't come back with a curing compound
Yeah.
and apply it on the shotcrete if it fits your job. I get it, it doesn't fit all the jobs.